Thank you for bringing us. I want to thank you for bringing us here for this lesson. We thank you for the teacher. You have blessed him with knowledge that is going to pass to us. Father, as we pray now, let us understand each and everything that is being shared in this lesson, that we may not need to always go through and we may not easily forget. Yes, in Jesus' name we have prayed. Amen.
Amen. Amen. Um, Today we are opening up proof by induction. Proof by induction. Some books refer to it as the mathematical induction. And to prove that the series is true or holds by mathematical induction, prove that the series does hold, is true, is consistent. We check series that their sums are true. To check whether the sum of a certain series is correct. To check whether a certain series holds a certain number of terms or any terms by the given sum. We do this by following the steps of mathematical induction. Step 1, we test whether the series holds with at least two terms. We check in the series the given terms, any two terms of its row. We check whether they can make sense or they still agree with the sum given. Then step 2 is what we call the assumption stage. At this point, we assume that the proof holds. Stroke the series is true for any constant value, stroke position. That assumption stage we normally denote it as n equal to k. And then step 3 is when we prove that beyond the k the series will still hold, or beyond that constant term the series will still hold. And the step 4, we perform the induction or stroke conclusion. Straight away, I would love us to brainstorm the idea as we do examples. So in the examples, 1, prove by induction, prove by mathematical induction, prove by mathematical induction, prove by mathematical induction, that prove by mathematical induction, that part A, proved by mathematical induction, that part A, the summation of R equal to 1 up to n over quantity R is the same as a half n into n plus 1. Proved by mathematical induction that summation or that series is correct. Its sum is true for any value of R from 1 up to n. It's advisable, if given such a summation, to generate the series. The learner should be able to generate the series. Generate the series out of that sequence or that summation given. How do you generate the series? Feed in R. When R is equal to 1, substitute here. When R is equal to 1, you have 1 as the first term. The series moves with a plus. When R is 2, the position you will take up will be 2. When R is 3, R reads 3. The equation expression is that one I've circled in blue. When R is 4, and so on, until when R takes up the maximum value, which is n. So R will still just take up n power 1. That series, when summed up, it's equal to a half n into n plus 1. That's what we want to prove. That is the series we want to prove. So step 1, test whether the series holds with at least 2 terms. So let's check at least 2 terms of this series. That series in blue. So we begin by checking the first term. That is when n is equal to 1 in the series. That's the first term. So the left-hand side, it is a term position. That's the first term, which is 1. But on the right-hand side, the series is waiting for you to feed in the value of n. So that is a half into 1 into 1 plus 1, which is actually a half into 1 into 2, which gives you still a 1. So you realize that the left-hand side is equal to the right-hand side. And this is concluded by saying proof holds. The series holds for the first term. The first term agrees with the sequence sum or with the series sum when you substitute n equal to 1. Still, checking whether it holds, I will check the next terms. When n is equal to 2, on the left-hand side, that statement is calling for the first 2 terms. The first 2 terms. On the left-hand side, first 2 terms, that is what and what? That is 1 plus 2. What is their sum? The sum of the first 2 terms. That is 1 plus 2, which is 3. But what does it mean? N equal to 2. What does it do to the sum? What does it do to the sum? On the side of the sum, you feed in n as 2. And that will give us a half times 2 times 3. When the 2 reduces, you get 3. So both sides still do balance. And what do we say? Proof holds. So after checking at least 2 terms, you can check 3. But when you check these 2 terms, these 2 positions, when you realize that proof holds, then you have right to go to the assumption stage. This is confirming that this series is true. Now let's check if n is unknown. At any position we don't know, what will happen? I want to confirm, I want us to agree that we are fine with these first 2 stages. Are we fine with these first 2 stages? The first is position of checking. I have someone.
Sir.
Yes, Benjamin.
So maybe I would like to see the question briefly again.
We are fine, sir.
Question is there. Proof by mathematical induction that this series holds from r equal to 1 up to
Yes, it's okay.
Of r as a half into n plus 1. Okay. Now let's go to the assumption stage. At the assumption stage, we say when n is equal to k. When n is equal to k. When n is equal to k, we say that assume assumption stage, as we call it, assume proof holds. Assume proof holds, and rewrite the series. So if it holds, then the series should be true for n equal to k. The series should be true for n equal to k. Where everywhere I had n, I'm going to substitute k in that series in blue. So up to n, so this time around it's up to k, will equal to this side where I had n, I'm feeding in the k. As we have said that we assume the proof holds. So that one is left at that statement. You don't do anything. about it. You leave it at that stage. Leave it at that stage. Assume true false.
Sir, help me and scroll up.
There.
Yes, sir.
Mark Sengova, can you unmute?
So, so what's the significance of leaving that statement of what's the significance of leaving it like that, just like that?
It is going to
That
help
statement
us.
in the blue,
Going to
the red
help
borderline.
It's going to help us when proceeding to n equal to k. When proceeding to k plus 1, it's going to be useful.
Yes, sir.
Yeah. Now, so proceedingly, why I'm saying it's going to be useful, when n is equal to k plus 1, when n is equal to k plus 1, this time around, we are not assuming, we are not going to assume. When n is equal to k plus 1, Dosh, what are you saying?
So like if when you scroll up on that
You are copying notes.
No, I'm just have a question there. So on the question. Yeah, there. So like on that what's I mentioned and what. So like on that window, that series you go to 1 plus 2 plus 3. Like how do you get it?
Dosh, be attentive, okay? Because
Okay, sir.
you were around when we are starting this. I want you to be very attentive. This is a summation from r equal to 1 up to n, and I said this is the equation, or this is the expression that satisfies this series. When r is 1, you feed r as 1 in this. That summation can be summation r equal to 1 to n of r squared, meaning it would now be 1 squared, and then progressing to 2 squared. Every value, every stage you go to, you feed in here to know which term you will have. Use it like that.
I've got it.
Okay. So when n is equal to k plus 1, when n is equal to k plus 1, it is, I want to emphasize this, when n is equal to k plus 1, it is a step away from k. It is 1 step away from k. And that will mean that you write the sequence or the series at k first. We are going to first move up to k, then exceed k by 1 step in the nth position. So this is the increment that is coming in beyond where we had stopped previous at the assumption stage. I don't know whether it's understood. That would be the procedure. That's the very important issue. You rewrite the sequence, but you don't stop now at k, you go up to k plus 1. But you already know this sequence up to k. The sequence up to k, we know it's sum. That's why I told you we are going to use it. The sequence up to k, we know it's sum. Its sum is a half k into k plus 1. But we are moving forward. We are moving forward beyond it by k plus 1. But what would we expect if we had gone up to k? What would the series become? if we had gone up to k plus 1, when we moved, remember, up to k, the sum changed. Where there is n, we put k plus 1. Similarly, one would expect that this time around still, where there is n, we should substitute k plus 1, which I should do, and say this will be a half into k plus 1 into k plus 1, but a plus 1 here. But this side, I'm reminding you that the summation, of the terms from 1 up to k, we already know its sum. That one, at least we know its sum. That one, this one here, we know its sum. From 1 up to k, just up to k, we know the sum. We already deduced it in the assumption state. So what is left is to see that these two sides balance. So this is the left-hand side, which must balance with the right-hand side for n equal to k plus 1. And that will be true, that we would have confirmed that proof holds at n equal to k plus 1. The other side, we should get a k plus 2. Should I proceed?
Sir, pardon on how you get the second hand side. I'm still confused about it.
How I get that?
Left hand side, I have k into k plus 1 plus k plus 1. Yeah.
Okay. Now, originally our sequence was ending at k, isn't it? At the assumption stage, it ended at k, not so?
Yes, sir.
Now we want to extend. We have just extended that we have just extended beyond the k by one step. So the term beyond the k will be k plus 1. This term beyond the k becomes k plus 1. By one step up beyond the k, it becomes k plus 1. The nth term becomes k plus 1, and that means the sum that was having n in it, since our nth term has changed to k plus 1, you know, the sequence, the term it ends with here is the term you take into the n values at the side of the sum. So if I end at k plus 1 this side, I feed k plus 1 the other side of n. When I ended at k as the nth term, it's what I took the other side, on the right hand side. Are you better?
Yes, sir.
So now, but
Excuse me, sir.
But yes, please.
So when you moved one step ahead with k, like when you got k plus 1, did you add 1 necessarily because r was equal to 1, or maybe that's just the policy?
It is in the steps we use. Maybe you missed the introduction. It's a step in the formula of proving by induction. The second last step is to prove that the series holds at 1 unit, at a known unit beyond the k, which is k plus 1. You see that?
So which means even if the sequence was 2, 4, 6, with that, still
it doesn't matter. As you're going to see in further examples. You see that?
Okay, sir. Yes, I see it now. Yes, it's now clear, sir.
All right, thank you. So we can go and proceed. We can go and proceed. So at this level on the left-hand side, we can, if you're careful, this is what I want to achieve. This is what I want to achieve. I must achieve this. I must achieve this from the left-hand side. So the work we have is to ensure the left-hand side becomes the right-hand side. So if you're careful, you will agree with me that we have an LCM here of 2. We have an LCM here of 2. So when you take the LCM of 2, you will have k into k plus 1 plus 2 into k plus 1. And that leaves us at a level of saying this is the same as 2, 2, and then you take out k plus 1, and then you have inside k plus 2, and that leaves you with the directly a half into k plus 1 into k plus 2. And you can agree with me that at this instant the proof holds. Since we have confirmed that the left-hand side is equal to the right-hand side at this point. Now, the last step in the steps we have is to perform the induction or conclusion. So how do we perform the induction? So therefore, we say that stage is this statement: since proof holds, for n equal to k, for n equal to, you start with the one you started with. For n equal to 1, we checked 1, we checked 2, then we assumed at k, and finally we checked at k plus 1. Thus, we are able and confident to conclude that thus the summation, as we were given, the summation from r equal to 1 up to n over quantity r is always true, and is summing up to a half n into n plus 1. For all, we can say for all values of n greater or equal to 1. Those conclusions are free as long as you give us up to this point. These other statements, you're free to leave them out or add them. Why am I saying from n greater or equal to 1? Because I've checked from 1 progressively upwards. I've not checked in the negative sense. Ladies, gentlemen, I know we have some ladies here. The proof doesn't hold if the proof wouldn't hold if this quantity at k plus 1 has not been able to balance with this one that I've circled in the oval way. If they didn't match, then the sequence wouldn't be true. Other series wouldn't have taken, wouldn't take it to be holding. The person who is asking that. Yes, Mark Sengova.
Sir, we have gone through 4 steps, and at each step we kept saying proof holds. Can't we just do one thing and then we know that the proof holds?
No, that conclusion step has been attached to a certain mark of conclusion for a long time. So that's why we call it a step as well. You must conclude and mention the series you've been proving again. It is a must appear lens. You must show. Okay. Part B. Prove that the series summation r equal to 1 to n of r squared is equal to 1 over 6 into n plus 1 into 2n plus 1. This time round, it's for square It's for square terms. This time around, it's for square terms. So can someone put up the hand and you tell us the series terms, at least 3 to 4 terms? Can someone put up the hand and you tell us the sequence, the terms in this series? Yes, Benjamin, you can unmute.
There is 1 squared, 2 squared, 3 squared,
Good.
4 squared.
Good. So what we have today at this point, the terms in the series would be 1 squared at r equal to 1. We have 1 squared. At r equal to 2, we have 2 squared. At r equal to 3, we have 3 squared, and so on, and so on, up to n squared, that upper value, up to the nth term n squared. That sum is equal to 1 over 6n into n plus 1 into 2n plus 1. So the approach doesn't change. We will follow the same arrangement. Check. When n is equal to 1, what does the left-hand side give us? It will suggest 1 squared, which is 1. What about on the right-hand side? We'll substitute a 1 times 1 there, times 1 plus 1, which is 2, times 2 plus 1, which is a 3. So I see 2 times 3, which is 6 over 6, giving us a 1. And we are good to say proof holds at that point. When n is equal to 2, the left-hand side captures the first 2 terms, the sum of the first 2 terms, and that will be 1 plus 4, which is 5. But on the right-hand side, the sum just waits for the value of n you've picked, which is 2. So that is a half times 2 times 2 plus 1, which is 3, times 2 times 2, 4 plus 1, that is a 5. So this 6 and that one cancel to leave us with a 5, and we are ably saying proof holds again, since the 2 sides balance. I don't want us to cram that they are just 2 steps always. A learner can say, when n is equal to 3, on the left-hand side, which terms do you take? How many terms will you add? Can someone tell us? How many terms will we add? How many terms will we add out?
3.
We'll add, switch on your mic and tell me what to what, which terms, from what to what in this series.
1 to 3.
Stephen, mention them. The first one is?
From 1 to 3.
No, I don't see 1 to 3. I see 1 squared, 2 squared, 3 squared. So it would be Amis, you can switch on your mic and talk.
1 squared.
1 squared.
Yeah. 2 squared and 3 squared.
Plus 2 squared plus 3 squared. That would be the expectation. So that means you're adding, this time round, you're adding 1 plus 4 plus 9, which gives us 14. Then on the right-hand side, that is 1 over 6 times n plus times n first, which is 3, times n plus 1, which is 4, times 2n plus 1. 2 times 3 is 6. We are using that expression there. We are feeding in here. N is 3. N plus 1 gives us a 4. Then 2 times 3 is 6 plus 1. That is a 7. That is a 7. So we are able to notice that we have a 12 here, and the 12 divided by 6 is 2. That 2 times 7 gives us 14. Gives us a 14, and we are ably saying again that proof holds. So the sides do balance as far as we wish. So we have no choice. We have confirmed that the proof holds for all the terms we were able to state. So at n equal to k is our assumption point. Assume the proof holds. Assume the proof holds. Assume the proof holds, and that would mean 1 squared plus 2 squared plus 3 squared, and so on up to n squared is the same as 1 over 6, not up to n squared, up to n squared, but taking on k. N is taking on k. That will be 1 over 6 into k plus 1 into 2k plus 1 at that instant. So when n is equal to k plus 1, when n is equal to k plus 1, what will happen? Which sequence will we have? Can someone switch on the mic and you highlight us there?
The sequence will be 1 squared.
Good. Plus what?
Plus 2 squared.
Plus 2 squared.
Plus 3 squared.
Plus 3 squared.
Plus, then we will add the,
and
then
so on
plus
up
k
to
squared.
what? Up to k
K
squared.
squared plus open brackets k plus 1 1 squared
Good.
will equal to 1 out of 6 open brackets. There are other brackets in there. It's k plus 1 plus 1.
K plus 1.
No, no, sir. Like the whole of k is replaced by k plus 1, then
Okay.
plus the 1.
There is a
Yeah.
first k here, which is taken up by k plus 1. Then here
Yes,
k plus 1,
k
plus
plus
1.
1 plus 1, then open brackets again. 2 into brackets k plus 1.
Okay.
K plus 1 plus 1.
Plus 1.
Yes.
So in other words, this is sum. In other words, the right hand side is equal to 1 over 6 into k plus 1 into k plus 2 into 2k plus 3. Do you agree?
Yes.
Okay. Someone is coming in late. So is it a must to check for all terms? No, it's not a must. You've just come in. It's not a must. You can check at least 2, a maximum of 2, or rather minimum of 2 terms is okay, but not 1, a minimum of 2. We have just checked 3 because on the first instance, we checked only 2. I've checked 3 to show people that you can go on as far as you can, but to save time, just check only 2 terms, a minimum of 2. So that is our right-hand side. I want to proceed with someone's submission here. So the left-hand side is 1 squared plus 2 squared. Before, Jordan has something that can't wait. Yes, Jordan.
Yes, I was asking, like, on the step before you wrote right hand side, like where I was saying, let me see. Yeah, where I was saying 1/6k plus 1. No, okay, the second last step, sir. The second last on the red part.
Okay.
Yes.
You are wondering how this comes about.
Yes.
This
Yes,
one
sir.
here.
Yes, sir. Yes.
We are feeding k plus 1 into this sum. Those your friend has used that replacing k, but we have fed k plus 1 in place of n everywhere. In place of n, in place of n. Huh? So this will be k plus 1 plus that 1 is k plus 2. Then 2 into k plus 1 is 2k plus 2 plus that 1, which becomes 3 there. You get it?
Yes, sir. Yes, sir.
Okay, thank you. Thank you. Okay, we can proceed. I want us to check whether the left-hand side will balance with that side we have got. So our left-hand side goes up to, well, after talking, please mute. Don't forget to mute your mic. Calvin, forgot your mic on. So after that, we want to check whether our left-hand side can take us to the right-hand side. However, I want us to remember that we know at the assumption stage, we know the sum up to k squared. The sum up to k squared, we know it. What's that one? Who can tell us that sum up to k squared? The sum up to k squared.
Sir.
It's 1 plus 1 into
1/6k into brackets k plus 1.
1/6k into brackets k plus 1 into what?
2 brackets k
into
2 plus 1.
plus 1. That is the sum. That is the sum up to, we have ended at k squared. That sum ends at k squared. Meaning we can't leave the other term at k plus 1 squared. We have to add it on. But our interest is to see that that side balances with our right-hand side. So I hope we do agree that there is an LCM to call for. There is an LCM to call for here of 6. LCM is 6. That will give us k into k plus 1 into k plus 1, 2k plus 1 plus the k plus 1 all squared. If people are careful, they will notice that I don't rush to
6. Size 6k like
6 here. Thank you. You realize that I don't rush to expand such that I don't waste time factorizing in many terms. So observe a common term here, k plus 1. If you're careful, k plus 1 is common. That leaves us with k into 2k plus 1 in plus 6 into k plus 1. I don't know whether we do agree.
Yes.
Good. And that can be that can be put down as 1/6 into k plus 1 into, expand that inside the term, into 2k squared plus k plus 6k plus 6. So at that instant, you just have to look out for that quadratic to factorize. Because of the 3 terms you need, you're remaining with the 2. They are in this quadratic you are looking at. This is 7k, this is 6. So we are looking at factors of 12 that give us a 7, and I think that is none other than a 3 and 4. That is none other than a pair 3, 4. So 3, 4 as a pair fed in there, what will happen? 3, 4 as a pair fed in there, what will happen? Let's see what will happen. And in yet a different color, let's use purple.
So I think it's a 6 and 1.
Yeah, 6 and 1, when you multiply them, you get 12. Have you checked this, ma'am, please?
So it's 3 and 4.
I'd forgotten. I didn't see that.
Okay, so that is the same as 2 squared plus 3k plus 4k plus 6. And that becomes 1/6. 1/6 into k plus 1 into, that can be a k out from there to get 2k plus 3. Then 4k and the 6, the factor is 2. When you take it out, you get 2k plus 3. And that shows us that we have 2 factors inside there. 2 factors inside there. And those 2 factors are k plus 2 into 2k plus 3. And if you're careful, you will notice that this is exactly the right hand side, k plus 1, k plus 2, and k plus 3. This statement is exactly the right hand side, which is the right hand side. So therefore, proof does hold again. Proof holds. So what is left for a learner is the conclusion stage. Conclusion. Since can say it in green. Since proof holds. Since proof holds for n equal to 1, 2, we went up to 3, k, and k plus 1. Therefore, it's true. It's true that the summation of r equal to 1 up to n of r squared is the same as 1/6 into n plus 1 into 2n plus 1, for that matter. That way. And those are the special summations, by the way. We have started with the special summations to mention. Is that first one, this second one, and the third one I'm yet to do. They are the special sums for integers, counting integers, square numbers, the counting domain, and the cubic numbers as our next example, which you must know. And I believe you need these ideas in our applied mathematics yet to come in discrete random variables. Teacher Alex will quote them. Just be on the watch. At a certain point, you will need them to move forward in probability.
Sir.
Yes,
Sir.
please. Yes, please.
So I mean, we must know that whole expression of what the sum is.
You don't need to cram it. You don't need to cram it because it is quoted for you in your tables. Understand? Okay. It's quoted for you in your tables, but you need to know what it is, how useful it is, and which topic it falls under, such that when you need it, you can easily look for it. Is it okay?
Yes.
All right. Example 3. Example 3, which is part C. We want to prove that the summation from r equal to 1 up to n of r cubed is equal to a quarter n squared into n plus 1 all squared. Or it could be given as 1 cubed plus 2 cubed plus 3 cubed, and so on until when r is n, of which the term will be n cubed. That sum is a quarter n squared into n plus 1 all squared. That sum is a quarter n squared into n plus 1 all squared. So at that instant, the process is the same. Set n to 1. That means on the left-hand side, capturing 1 cubed, which is 1. On the right-hand side, you're capturing a quarter into 1 squared into 1 plus 1 all squared, and that will be 1 times 2 squared, which is 4 over 4, which it will be still giving us a 1, and we say proof holds. Set n to 2, your next testing stage, checking stage. This is 1 cubed, means take 2 terms in the sum. That is 1 plus 8, giving us a 9. On the right-hand side, what does it suggest? It suggests a quarter times n squared. 2 squared is 4. Then 2 plus 1 is 3. Square it, you get 9. There's 4's reduce, and we'll still get 9. And we say proof holds. Even if you don't mention the word, it's evident. Set n to k. Set n to k. At that point, assume proof holds. Assume proof holds. And what does the series become? 1 cubed plus 2 cubed plus 3 cubed plus up to when n is taken up by k, until n is taken up by k, which is equal to a quarter k squared into k plus 1 all squared, for that matter. And then the proof stage is when you set n to k plus 1, set n to k plus 1. That means the series will progress. The series will progress up to k plus 1, beyond the k, up to k plus 1. And the sum also achieves the k plus 1. In place of n, it achieves a k plus 1 all squared into k plus 1 plus 1, this instead becomes k plus 2 also squared. However, this means you already have a right-hand side. You already have a right-hand side at k plus 1, which is a quarter into k plus 1 squared, k plus 2 again squared. But the left-hand side, however, the left-hand side has a statement 1 cubed plus 2 cubed plus 3 cubed plus until k cubed. This word here, we know it's sum, but we are moving to k plus 1. So the known sum is there as a quarter. The known sum is a quarter into k squared into k plus 1 squared. That's the known sum, which we are adding a k plus 1 cubed. So that's the left-hand side, which we must match with the left-hand side, which we must match with the right. LCM is a quarter. Common term is k plus 1 squared. So inside there, I remain with the k squared plus k plus 1 multiplied by 4 there. Do we agree, class, with that factorization?
Yes.
That's wonderful. That's wonderful. That becomes k plus 1 all squared out of 4 into k squared plus 4k plus 4k plus 4. If you are good at observing perfect squares, that is a perfect square. That's a perfect square. K squared plus 4k plus 4 is a perfect square. K plus 2 all squared. It's a perfect square. You can go ahead to factorize, but if you're observant, you would mention that it's a perfect square straight away. So that becomes k plus 1 all squared over 4 multiplied by k plus 2 all squared. If you can check. So that implies the left-hand side has also become a quarter into k plus 1 all squared into k plus 2 all squared, which is a matter to mention that proof as well holds, since it agrees with the right-hand side. That one in red, they do agree. So lastly is to draw a conclusion that since proof holds, for n equal to 1, 2, k, and k plus 1, it's then true. That the summation from r equal to 1 to n of r cubed is equal to a quarter n squared into n plus 1 all squared. Conclusion stage is a matter of point also to see. It's a matter of point to be seen. Every time they add in some statements for learners to include, we can keep graduating, but as long as you know how to induct, how to perform the induction step. Excuse. Unless otherwise, generally it's important to note Those are important summations. Note, one, that the summation from r equal to 1 up to n of r is a half n. We have proved that they are true. Those are important summations to note. 2, the summation from r equal to 1 up to n with their square terms or square numbers in the counting domain. It is the sum is that one. And 3, what if they are cubic? What if they are cubic patterns, cubic numbers in a series in the counting domain? That is a quarter n squared into n plus 1 all squared. That's the conclusion we have drawn from the steps or from the stages we have gone through. We have confirmed that those are true. We have confirmed that those are true. We have confirmed that those are true. So I'm requesting you repeat for me on how you added the k plus 1 on the right hand side. On the right hand side, I didn't add any k plus 1. On the right hand side, I didn't add any k plus 1. Rather, I substitute k plus 1 in the sequence. Owen also has come in a bit late. You substitute k plus 1 in the sum sequence, in the summation. So at k plus 1, the sum takes up n as k plus 1, k plus 1 plus 1 all squared. So this becomes a plus 2. That's how we have it down there. Just substituting that expression of the sum. Owen, hope you helped as well. So that is the conclusion we have drawn. Those are important sums that we must keep around us. The good news is we have them in our tables for us to easily quote, but you know their usefulness and their sequences. If you see them, then you should know that such terms up to n, they are summed up as a half n into n plus 1. Such terms, but when squared, 1, 2, 3, and so on, when squared up to n, each term squared, you get that sum as 1 over 6 into n, n plus 1 to n plus 1. The same happens if each term is now power 3, but up to n, the summation is a quarter n squared into n plus 1 all squared. I want us to have a situation if it's not any of these three general ones. I want us to have a situation if it's not any of these three general ones. If it's not any of these three general ones. If it's not any of these three general ones, what will happen? If it's not any of these three general ones, what will happen? And we are going to involve some trigonometry. We are going to involve some trigonometry. I hope someone who wanted me to scroll back there, that person is done. Okay. Example number 2. Example 2. Example 2. Example 2. Prove by induction. Prove by induction that. Prove by induction that cos theta plus cos 3 theta plus cos 5 theta plus cos 5 theta and so on up to the nth term, which is cos 2n minus 1 theta is equal to sine the sine of 2n theta divided by 2 the sine of theta divided by 2 the sine of theta. That's our next example. Our lesson is soon ending. Those asking for break, we just relax. Our lesson is ending in the next bit of 13 minutes. So we have those terms we want to prove by induction. The approach remains the same. The beauty is that this time around the series has been denoted or stated for you. It has already been stated for you. So you begin by stating or checking whether it is true. When n is equal to 1, the left-hand side has the term cos theta. The right-hand side has the term sine. N is 1. N is 1, you will have sine 2 theta over 2 sine theta. But from double angles, that sine 2 theta is the same as 2 sine theta cos theta over 2 sine theta. When 2 sine theta cancels, you get cos theta again. So I'm right to conclude that proof holds at that instant. I'm referring to trigonometry. Let me hope someone is on. Let's go to the second term. Let's push as far as the next 2 terms. When n is 2, the left-hand side suggests cos theta plus, we add it up to the second term, that is cos 3 theta. And this being a summation, I can add I can interchange to have the bigger angle first. When adding cos's, we get 2 cos 3 theta plus theta is 4 theta over 2, that is 2 theta. Then subtract them times cos the difference. 3 theta minus theta is 2 theta over 2, that is theta. On the right-hand side, in the same arrangement, what will happen when we feed in n as 2? The upper term will be 2 times 2, which is 4. And we will have sine 4 theta over the 2 sine theta. Over 2 sine theta. Over 2 sine theta.
Sir,
yes, please.
sir, that on the left-hand side, I've not understood what you've done.
What I'm doing is trigonometry. You want me to remind you about factor formula?
Yeah, we have not studied about that. Some of us, it's our like so.
When adding cos's, cos A, let me make a statement here to refer to. When adding cos's, we get 2 under factor formula, we get 2 cos A plus B out of 2 multiplied by cos of A minus B out of 2. So that becomes up here 2 cos 3 theta plus theta out of 2 multiplied by cos of 3 theta minus theta out of 2. That way. Is it okay now?
Yes.
Good. That's good. That's good. So that one becomes, if you're careful, you say 4 theta over 2, which will be 2 theta. then a 2 theta over 2, which will be just theta. Then this side I have a sine 4 theta. Apply the double formulae, that will be 2 sine 2 theta cos 2 theta over the 2 sine theta weighting. Apply the double formulae for sine 2 theta again, to sine 2 theta again. You will get 2 sine theta cos theta, multiplying cos 2 theta weighting, then down here 2 sine theta. So the 2 sine theta, if you're careful, the 2 sine theta cancels out. This 2 sine theta will cancel out, and you will get 2, this 2 here times that cos 2 theta times that cos theta, and you get cos 2 theta multiplying it by a cos theta. And at that instant, the left-hand side is equal to the right-hand side. So we are yet to say here that the proof again holds. Proof holds, but some trigonometry concepts were required. So when n is equal to k, assume it holds. Assume it holds. So the series will be cos theta plus cos 3 theta plus cos 5 theta plus, and move up to when the nth term is changed by n to k, is changed from n to k, and the sum becomes sine of 2k theta divided by 2 sine theta, that order. So that is the statement when n is equal to k. That is the statement when n is equal to k. That's the statement when n is equal to k.
Excuse me.
Using the chat, please. Your network is not okay.
Excuse me, sir.
Please.
Excuse me, sir.
Yes, sir. Yes, Samuel. Yes, Samuel.
So I'm not getting how we are using the n in that question.
How we are using n?
Yes.
At which point?
Like that point where we said n is equal to 1, n equals to 2.
Were you here at the beginning?
Yes, I was there.
Yes. We are using it the same way. In the sum, I feed n here. I feed n here. When n is 1, 2 times 1 will remain at 2. Though for me to make the two sides the same, I apply some trigonometry. Then anything when n is 2, that will be 2 times 2. That's how we came to a 4 theta there. Somewhere. Hope you're okay.
Okay, I think I've got it. I'd not seen the question.
You had not seen the question.
I had seen, but I had not seen.
The good thing, Joshua, I was answering Joshua next. He has recovered. He has seen also that the nth term is cos 2n minus 1. So at k, that n is replaced by k. And even the n in the sum is replaced by k. And we assume it holds at that step, at that stage. So at our conclusion stage,
so you're missing. So you're missing.
So what about the theta?
So you're missing a theta on the Gundi.
Yeah, yep, it must be
On
there.
the cos 2k minus 1.
You're right. It must have a theta. Thank you. That's good. It must have a theta attached to it here. Good. Yeah, now people are on. That's good. Thank you. When n is equal to k plus 1, what will our cell be? Cos theta plus cos 3 theta plus cos 5 theta plus. It will progress up to the nth term. Here, I want someone to give me the term after this one. The term after this one, what will it be? What will the term after that one be? What will be the nth term at k plus 1?
It's cos 2k plus 1
2k plus
k
1, like that.
plus 1, yes, theta.
Theta, perfect. That person has replaced n back to the series to explain to someone that n has been replaced by k plus 1, 2 into k plus 1, but there is a minus 1 waiting before theta comes in. So 2 times k is 2k, 2 times 1 is a 2, minus the other one. That's why we have a 2k plus 1. Someone who may be lost. That short is for you. Okay, back here, that becomes our nth term. Now the sum as well takes up the same k plus 1 as n, and the denominator didn't have n in it, but the numerator has n in it. It will be sine 2, where there is n, put k plus 1 times theta. That would be our right-hand side. But on the left-hand side, we are aware that the summation is summation from theta up to that point. From theta up to that point, we know it. It is sine of 2k times theta over 2 sine theta. This is now my left-hand side. But I'm adding on the nth term at k plus 1, which is 2k plus 1 theta. But the right-hand side, which I must balance with, is sine of 2 into k plus 1 theta over 2 sine theta. Now, beyond this, it is trigonometry to react. LCM, the LCM in this case on the left-hand side is 2 sine theta, if you do agree. The LCM is 2 sine theta, 2 sine theta, which will leave us with a sine of 2k theta plus that quantity hits the other bracket to give us 2 cos of 2k plus 1 theta multiplied by sine theta. Multiplied by sine theta. Multiplied by sine theta. There we are. Jordan Kasozi, can you unmute and mention that what you want to say?
Yes, I was asking that what if you just put 2 sine theta instead of 2 cos in brackets
okay.
2k plus 1?
It's okay. A product has no problem. Any term can start. That wouldn't be a question. A product, any term can begin, okay?
Yes, sir.
Okay, now at this level, we have a situation. We have a situation in 2 cos. Why I've started maybe to mention something to you, Jordan. The reason as to why I've done it like that, you would not see it later if you started with a sine. But me, I was able to observe that of the 2 angles, theta and 2k plus 1 theta. 2k plus 1 is bigger than this 1. In sine, the coefficient of theta is 1. Here it's 2k plus 1. So I've started with the bigger angle ratio. So in that case, we are going to apply the factor formulae again, but in reverse. Yes, Owen?
It's okay.
All right. We are going to apply the factor formulae, but in reverse. I want you to know that let's recall. There's some information I want us to recall. Back in trigonometry, there are situations where we subtract signs. When we subtract signs, for example, sine A minus sine B, we get 2 cos of the sum. The bigger angle is in cos multiplied by sine of A minus B over 2. So what we have right now is that statement, 2 cos times sine. But how do we go back the other side? How do we go back to these 2 sine functions? We go back by writing, when reversing, when you notice that you have this kind of statement, when reversing, write sine and get these angles in the product, sine of the sum of those angles, minus the sine of their difference. But check the sum, it will give you the A back. B over B is negative, and somewhere it's positive. So the B cancels, A over 2 plus A over 2 will give you back the A. So I want us to reverse this. Since it's a product of sine and cos, but cos has the bigger angle, it means originally in factor formulae, they subtracted the sines. Let's be patient with the factor formula. Those who are not yet there, you will need these ideas to be able to agree with me. So reversing, I will write sine, then I get the 2 angles, 2k plus 1 theta plus theta. The angle here plus this angle in sine, minus, it is subtraction of sides. So minus, let me take this away, minus sine of the 2 angles, 2k plus 1 theta minus theta. That's what we call the reverse process of factor formula. Because in my proof, I need sines. Having seen a cos, I was forced to reverse. Someone may ask me, how did I know that I had to go to factor formula and reverse? The right-hand side I'm looking for has sine over sine. Sine 2 over 2 sine. So having seen a cos here, the factor formula reverse process would help me clear it and into 2 sines only. So this is over 2 sine theta. This is the same as 2 sine theta down here, 2 sine theta, and this becomes sine 2k theta plus sine. When you simplify this, you get sine 2k plus 1 plus the other. When you realize that this is 2k plus 2 theta, when theta goes out, minus sine of 2k, this is the same as 2k plus 1 minus 1. When you again put out that theta, so that cancels, that 1 cancels and remain with that, which in note says that sine 2k theta will go. And the learner will have no choice but write the same term as it is in the right-hand side. That, therefore, our left-hand side also is equal to sine of, if that 2 goes out, you'll get k plus 1 theta divided by 2 sine theta, which is exactly,
Excuse me, sir.
please.
So how have you got the sine 2k plus 2 theta?
Oh,
On adding those thetas, theta plus theta.
okay. Let me show it to you here. Expand here, 2k plus 1 plus 1. I've put out theta. There are two options that way, or you just expand it, 2k theta plus that theta. This will be 2 theta. 2k theta plus 2 theta. Then you take out theta. You end up with 2k plus 2. Is that so?
Yes, sir.
Okay. Thank you. That's how we reach there. And we have finally got the right-hand side, which is a confirmation that, again, proof does hold. Proof holds. So since, to confirm, since proof holds, for n equal to 1, 2, k and k plus 1, and k plus 1, and k plus 1, then it is true. Thus it's true. Thus it's true that the cos theta plus the cos of 3 theta plus the cos of 5 theta up to the nth term, cos of 2n minus 1 theta is equal to sine of 2n theta divided by 2 sine theta by mathematical induction. Ladies and gentlemen, in this call, I wouldn't love to go beyond this stage, but otherwise, I wish you a practice session that is good, that will help you brainstorm. And today, I must send the full document with the last subsection as sums of series for us to continue our discussion series to the end. I would love that before the next lesson, we do sums of series and complete it as well. We need one more example or two on proof by induction. We need one more example or two on proof by induction for us to proceed to sums of series and close the chapter series at this note. I want to thank you for listening and adding me those extra 10 minutes when you're still on up to this number. I want to wish you a nice week.
Excuse me, sir. Excuse me, sir.